Okay, so what we have tried is here is the like we can say we have put this values. So q by k upon under root of 1 minus r square whole square plus 2 eta r whole square, where this lambda square by omega square is nothing but your r square, and you can say this is MEM. So I am putting, you can say M will go on this side. So this will be XM upon ME is equal to R square upon under root of this, right? So this will be coming. So now this particular term, right? This particular term, I'm supposed to say it is my DMF, right? In the previous equation, if you see, the value will be in place of R square, your value is 1, right? So your DMF equation for harmonic excitation was coming, that is a 1 upon under root of 1 minus R square upon 2 eta R whole square. While in this case, there is a R square term has been coming because of this rotating imbalance. Now, for the same way, you are going to develop this particular curve of DMF versus R. So again, in the same way, you can use this equation. Like for first, you can take the case of eta is equal to eta is equal to 0, and then you take the different value of R. So starting from 0, 1, 2, and so on, right? And so on. So if I starting with here, so eta is equal to 0, R is equal to 0. So means this. So R is equal to 0, 1 minus 0 is 1. This is 0, and R is equal to 0. So 0 minus something is 0. Right? 0 upon something is 0. So this will be 0 only. If you see the previous equation, the curve should be started, curve is started from 1. While in this case, the curve is starting from 0. This is what the changes has been actually brought in while you are plotting the different DMF versus frequency ratio for different vibrating systems. So for each vibrating system, you need to develop this particular curve for designing your foundation systems, right? So then you can go further. You can take the value of R is equal to 1, eta is still equal to 0. Then you will reach to the infinity. And then so on, you can plot this particular curve. But this curve will never be less than 1, right? So this value of DMF will never be less than 1. So you can see this. In a previous case, it is approaching to the 0, right? But here it is approaching to the 1, right? If you see, if you just take out this all the value, then you will see that this 1 value, then this is not reaching, this is approaching to the 1 value. Then you can take the different value of eta. Eta is equal to 0.1, 0.2, 0.3. For each value, let's say for eta is equal to 0.1 and R is equal to 0, 1, 2, and so on. You can plot this particular curve. So if I take this R is equal to this curve, then if you plot this, then you will reach this thing. Okay, this value will be, this curve will come. Then when you take eta is equal to 0.2, eta is equal to 0.3, then so on, this value will be coming. So if you see here, now this peak is been coming, which is on right side of the 1. In the previous case, what is happening? Your peak is been on the left side of the you can say the 1. Here it has been coming right side of the 1. Previously, this peak has been increasing in this way. Here, the peak is going in this way. As I'm increasing the value of eta, my value is coming in this way. As in a previous case, if I'm increasing the value of eta, my value of peak is increasing in leftward side of this 1. This is what the difference in this DMF and the previous DMF due to one eccentric mass is been actually coming. So whenever you plot, you please keep this into the mind. This DMF curve will going to change for each vibrating system. You need to develop this particular curve for each and every vibrating system in this way. Similarly, you can plot at what value of R your DMF is maximum. Same way. So if you can take D by DMF with respect to R, then this value will be this value. If you take the derivation of this, then this value of R will be coming 1 upon under root of 1 minus 2 eta square. In the previous case, if you see the R is equal to just it is coming under root of 1 minus 2 eta square. While in this case, this value has been changing. If you put this value of R into the original equation, that is r square upon this value. If you put this r is equal to in this equation, then you will get the maximum value, which is this. Based upon that, you can plot this particular curve for any single value, and you can find out what is the zone of different places. So this is my DMF. This equation will give you the maximum value of DMF for different value of eta, or a particular value of eta, and value of r for corresponding to this you can calculate from this equation, right? And as I say, for this value, my eta my r value is become maximum, which is on the rightward side of 1. Similarly, in the same way, you can also plot this particular Mexwell diagram. The procedure what we have simplified is the same as what we have seen last time. Same way you need to plot it, this Mexwell diagram, no changes. Almost it is a similar line, but you can plot this particular curve in the same way, right? So this is what is explanation with, you can see the eccentric loading, mass with the eccentric loading, and thereby I'm completing the entire syllabus of earthquake engineering with this. If you have any questions, I'm ready to take it. I already share the PPTs with you, right? So this way we are concluding all the syllabus.